Okay, so welcome to the 23rd video in the Discrete Structures series, and this video is going to be a continuation of our chapter Logic and Proof Methods. We started this chapter a couple of videos back, and we have already covered propositional logic. And so in this video, we'll be looking into the idea of propositional functions and predicates. And here we'll see the definition of propositional functions and see how propositional functions help converting predicates into propositions. Then we'll move on to the idea of quantifiers, and we'll look at it with a perspective of a tool that also helps convert predicates into propositions. The next thing that we're going to look at is going to be a quick overview on the precedence of quantifiers. And this is basically about a convention that says that any quantifier comes in a higher precedence than any logical operator, like conjunction, disjunction, and negation. We'll show with an example later, but continuing with the scope of the video, the last topic that we're going to look at today is going to be binding variables. And we'll look at the scope of quantifiers and variable usage. Okay, with that overview, let's begin our discussion with predicates. I want to recall two sentences that we used earlier in our discussion of propositions. Let me write them down quickly. So in our discussion of propositions, we considered both of these sentences in the same category. We simply said both of these are not propositions because their values could not be resolved into a true or false. And we were in fact correct in our reasoning. What time is it is a type of a question that cannot be resolved into a true or a false. And we reasoned similarly for this one. We argued that without the values for x and y, we couldn't really tell if this statement would be true or false. So we simply said that both of these are not propositions. But if you think about it, the nature of this sentence is definitely different than this one. We can never resolve this sentence, what time is it, into a true or false, because it is not the nature of this sentence to be resolved that way. But if I look at this one, something's definitely different. Because all I'm missing is the values for x and y, and once those are given, this exact statement will be able to be resolved into a true or false. So there arises a necessity to study these kind of statements, and we call these predicates. So a predicate is any statement that cannot be resolved immediately into a true or false, but it could be if the values for its composing propositions were resolved. And if I look at this statement, x and y are my subjects, and this part greater than 3 is my predicate. So in that sense, it is similar to the idea of predicates in English grammar. And I am just mentioning this vaguely based on my research of a few textbooks, but our takeaway should be that a predicate is any statement that cannot be resolved into a true or false until we have values for its propositions. And that process of assigning values to these variables and converting this predicate into a proposition is done using something called a propositional function. So let me represent this entire statement as a propositional function. Let me write a function p of two variables x and y is given such that x plus y is greater than 3. And by definition of a function should take some inputs and generate some output. And since this is a propositional function, the output of this function is actually a proposition. To make sense of that, let me see what happens if I plug x as 1 and y as 2. When I plug the inputs of 1 and 2 to my propositional function, it will spit out a proposition to me. And that proposition will look like 1 plus 2 is greater than 3. And you can tell that this is a proposition because I can resolve it immediately. It is just stating that 3 is greater than 3. And that is false. And if I were to plug other values for x and y, I would get other propositions that could be resolved similarly into a true or false. For example, if I change this 2 into a 3, I get a 4 is greater than 3, which is now a true proposition. So a propositional function can be defined as a function whose inputs are the variables in the predicate and whose outputs are a family of propositions that are all derivable from the given predicate. Therefore, we want to view propositional functions as a tool that help us convert predicates into propositions. And to let you know, there is another method that also helps convert predicates into propositions, and they are called quantifiers. Okay, so let us also begin the idea of quantifiers with an example. Let me write a couple of sentences here. So I've written two sentences here. The first one says that every computer is functioning correctly. And assuming computer 1 is one of the computers in this grid, can I say that computer 1 is functioning correctly? I definitely can, because every computer is functioning correctly means computer 1 being part of the network is also functioning correctly. And from this sentence, computer 2 is hacked, I can successfully infer at least one computer is hacked. But the problem is that the idea of the propositions and the predicates and even propositional functions are not able to represent these kind of sentences. Because so far we are only able to tell if something is true or something is false. But we do not yet have a way where we have a collection and we want to refer to some or all items in that collection. And this happens a lot in practice. Everybody is present in class today, for example. Or at least some student is absent. In other words, I need to be able to quantify the items in a collection. I want to be able to write propositions like every item in this collection should have this property, And similarly, I should be able to write some items in this collection have this certain property. We mean that there exists at least one item in the collection that meets the property. So whenever I mention some, I'm quantifying existentially. And when I say every, I mean that every item in this collection should meet the property. So I'm quantifying universally. And these quantifiers have special symbols. The universal quantifier uses this symbol. So this is for the universal quantifier, and it's often read as for all, for each, for every, and so on. And on the other side, we have our existential quantifier, which is represented by this symbol. It looks like a flipped E, and this one is generally read as some what there exists. So let's have a look at a couple of usage examples. Whenever I write something like for all x px, I'm essentially claiming that px is true for all values of x. And similarly, when I write there exists x px, I mean that there exists at least one x that meets the criteria. But you should always be aware that every time you use quantifiers, you should be aware with the idea of a domain. Because when I write for all x, it's not enough. X in what? Let me show you an example. For all x, x square is greater than or equal to 0. We might agree that this statement is correct because whatever number I choose for x, once I square it, the result is going to be greater than 0. But then I square is minus 1 and that is less than 0. So that means if I use I for my x, this statement is not true. And so it's important to say that x belongs to a real number set. And now it's valid. For every real number, the square is greater than or equal to 0. And so this set of real numbers provide all the values x could be. And that is called the domain of the quantification. And you should easily see that the same thing would also be true when I'm writing an existential quantifier. And once you know domain, the idea of a restricted domain is also widely used. Let me say I want to write this statement, x square is greater than x. But I know that this is true only in certain cases. If I plug x as a 0, it doesn't work. 0 is not greater than 0. And when I plug 1, it doesn't work either. Because 1 is not greater than 1, it is equal to 1. But as soon as I start plugging numbers from 2 and beyond, this equation starts to hold. So I might want to write for every x greater than 1, and x would be a real number, and I would want to claim that x square is greater than x. And this would be a valid quantification. And you see how I use the idea of a restricted domain. I took a bigger domain of real numbers and then I restricted it to values greater than 1. So you'll find this pattern used all over mathematics. And let's see one example for an existential quantification. I could say there exists a real number x such that 1 added to that number would give a 2. Because from the entire set of real numbers, 1 is only such value that will satisfy this equation. But that's good enough for me because there exists only requires one value to support my predicate. But if I were to change this there exists into for all, now it would definitely be incorrect because all real numbers added 1 is not equal to 2. So I think you'll be able to appreciate how these tiny symbols help us represent such complex sentences with such precision. And I also teach this at the start of the video. These quantifiers are converting these predicates into propositions. So this is a second way of converting predicates into propositions. When I say x plus 1 equals to 2, I cannot tell if it's true or false without knowing the values of x. But if you quantify it, that is if you say there is at least one x that satisfies the equation, it then becomes a proposition because now it can be resolved into a true or false. If there exists one, it is true, otherwise it is false. And similar is the case with the universal quantifier. It also converts a given predicate into a proposition by quantifying the domain. Okay, and next we'll look at how we can prove or disprove statements that contain quantifiers, and this is going to be extremely relevant for our discussion later in proof methods. So this is quite logical and simple, but we need to know it. So let's think about it. I have this proposition for every x px, and I have this one. There exists a x px. What does it take to prove this? See, I want to prove that px is true for all values of x, okay? So in order to prove this, I'll need to prove exhaustively. That means I'll have to go through each possibility of x and verify that it works for all of them. But if I need to disprove it, I only need to find one example for which it doesn't work, because the claim it has to work for everything. So if I can find one counter example, it is enough to disprove a universal quantification. Okay, if the claim says that it is true for all, I only need to prove that it is false for one. But in order to prove it true, I need to prove it exhaustively for everything. And here you would have guessed it, it is just the opposite. If I want to prove there exists a x for which something is true, I can just find one example. And that one example will complete the proof. Remember earlier when we said there exists a x for which x plus 1 is equals to 2. And I only need one example to prove this, and that example is just a 1. And similarly, when I converted this into for all x, x plus 1 is equals to true, I am in this paradigm. And I know that this is false. And in order to prove it false, I only need one counter example. Let's say 4 is that counterexample because 4 plus 1 is not equal to 2. So this is really simple but really important. And what does it take to prove this? Because the argument here is that Px is true for at least one x, in order to prove it wrong, you'll have to prove it that it is wrong for all of them. So you'll have to disprove exhaustively. So exhaustively just means for all of them. So next we have a couple of very short topics and then we'll end the video for today. We have precedence of quantifiers. And this is again just a matter of convention. Let's say I have this proposition for all x, Px or Qx. So the convention that we will use is that the quantifiers for all and they exist will have the highest precedence. So if you look at something like this, it means that for all x, Px or Qx, okay, Qx is a separate proposition which is not contained within the scope of this quantifier. And if you want to mention that Px or Qx should be true for all x, you want to write it this way. And now I have applied this scope and which tells that the for all x applies to this entire statement. So this is one thing that you should know. If there is no parenthesis, you should only associate the quantifier with whatever is attached to it. But again, this is just a convention and we don't spend much time with conventions. So let's move on to binding variables and scope in fact. So let me demonstrate this with two examples. Let me write them down first. Okay, so this one says there exists a x for which x plus y is equal to 1. The variable x here is bound to this quantifier there exists. So therefore this is called a bound variable. And y in our case is a free variable. Remember earlier we talked about domain. When I say for all x, there is a domain. Now it is true that the domain is not often mentioned and should be understood implicitly, but it is the same as saying AB is A times B. Even though there is no multiplication sign, you should understand that we are taking a product here. Similarly, every time I do a quantification, you should understand there is a domain. And therefore my variable x is going to be bound to that domain. Because this could be for all x in R. Okay, for all x greater than 3. And whatever that bounding domain is, my x is going to be bound. On the other hand, the value for y is going to be free. Therefore it's called a free variable. So you could say that in any proposition that makes use of quantifiers, the variables used in the quantifiers are called bound variables and other variables are said to be free. And with this example here, I want to demonstrate an idea of scope. So this proposition is essentially stating that there exists at least x for which this statement is true. And then it's just saying or for all x some other statement is true. And the big takeaway here is that this x is different from this x. Because this quantifier only has its influence in this range, the variable x also has its influence only in this range. Therefore, if I were to just change this x into a y, it would be exactly the same proposition. And I hope this is somewhat sensible to you. If you have some programming experience, it should be, because in any programming language, I'll refer to JavaScript, we have these blocks of code that are scoped. I could write a for loop this way, for I is equals to 1 to let's say 10. And once I terminate this loop, I can use the variable I for another loop again. I could again say for I is equals to 1 to 100. And I do not need to initialize a new variable because the scope of I is limited to the scope of the block. And before someone points me out, I want to mention that var would not work that way. It would actually be hoisted to the top of the function. But my point is not that here. When you use late and const, the variables are scoped. But that is entirely not my point. My point is just to give you an idea of what scoping is and how it works with quantifiers. Okay, with that discussion, I'll close the video for today. In the next video, we're going to discuss the logical equivalences in predicate logic, the negation of quantified statements, and nested quantifiers. So I can't wait to see you guys in the next video. Have a good day and bye.